So good evening, everybody. Welcome back to the first lecture. Welcome to the first lecture of EE 520. Today we will introduce the course a little bit, and then we're going to discuss somehow just a generic problem that is we're going to approach toward the end of the course. And by discussing this element, we will know why we're doing what we are doing. Okay? So the course title is Power System Steady State Analysis. So it has the word power system. It means anything that is either distribution or transmission or generation. Steady state analysis. What does a steady state mean? Steady state means over a few cycles ahead. Not the exact cycle where we open the breaker. When we open the breaker, for example, this is transient. And to model the transient, we need computers that simulate the waveforms across small time steps. For example, we have real-time digital simulators. Are you familiar with RTDS? Who is familiar with RTDS? So RTDS is a real-time digital simulator or electromagnetic transient simulators where they go over small cycles. But we're not looking at that. We look at steady state. It means we look at over multiple cycles. What is the implication? The implication here is we care about phasors. What are the phasors? You estimate phasors between different cycles. That's very important. Steady state means not during the exact incident, over a little bit few cycles. It could be 20 cycles, it could be 30 cycles. So if one cycle is 1 over 60, which is what, 16 milliseconds, how many 10 cycles? If one cycle, so let's use 60 hertz. If one sinusoidal signal is 1 over 60, what is 10 of them? 16 milliseconds. What is 10 of them? Multiply by 10. 166 milliseconds. So what's 166 milliseconds? Almost 0.166 seconds. So you can see in 10 cycles that's almost 0.1 or 0.16 second. That can be a steady state after some time. Transient, we look at less than the actual sinusoidal signal. So we're not going to look at in this course the exact. We're going to look at when the system is stable, how we run the power flow problems. Okay? We also, in this course, again, the textbook is Power System Analysis, which is the same textbook used in EE 463. EE 463, which is undergrad course. It's relatively one of the easiest courses. It's the easiest course in power system because it teaches you the basic concept of power system. Now, the course description is here. Let's go over the content. So when you have the textbook, the best way is to try to cover the concept in a general level. So for example, once we start with the basic concepts, which we're going to start next lecture, we're going to cover, I'm going to ask you to look at chapter 2, section 3.2, 3.6, 5.2, 5.3, and the per unit system, where you look at, for example, those two sections. Try to read the textbook, understand what is meant by that. I'll provide the slides, inshallah, in the appropriate time. So basic concepts and per unit system, it will give you the first step, especially those who don't have power system background. It will give you the first step in conducting these calculations. And then we're going to do about power system matrices. What is the admittance matrix? How do we connect a network of line in a big matrix? How we do the operations in those matrix operations? So are you familiar with matrices, Mustafa? Are you familiar with matrices? So how we construct the power system matrices? Then we're going to talk a little bit about state estimation on a separate note, how we estimate the states of the system using selective measurements. We're going to run the power flow analysis, balanced faults, and unbalanced faults. using symmetrical components, and then lastly we'll touch a little bit about stability. Why we are doing 1, 2, 3, 4, 5? To each of these systems, the ultimate goal is to know whether the system converges or not. For example, if we have generator A, generator B, generator C, and you work with the utility, you run economic dispatch, for example, or you run power flow, then you allocate. In generator 1, I'm going to have 1 megawatt. Generator 2, 3 megawatt. Generator 4 or 3 megawatt. 3 generators. Is this power contribution to the grid, would it make it stable? Would it converge? Would it be optimal, for example, if we run optimal power flow analysis? So our goal is to look at the system level. That's why, if you read here, we analyze large power systems. 6 bus, 9 bus, 32 bus, etc. Okay? The camera is working? Okay. So let's touch a little bit. Let's touch about this first, just talk. So introduction to power system stability. This is the just warm up. It's not technical, but it shows you our ultimate goal, and then based on that we can start taking the concept more and more. So there is energy will intuition. We're going to introduce this concept today, and yes, in the exam I might ask theoretical questions. Explain why, not only problems. The delta limit, PV cares for a 2-bus system. That's a simple system. So I'm going to start with the objectives of very short handout is to explain the stability using potential energy will and analogy, like how this will explain. The second concept is we need to distinguish steady state from transient. That's very important because we're covering steady state. And what is the power angle and stability limit in power system? We need to derive PQ for 2-bus network, and we try to solve VB, bus B, we have A and B, as well as compute the maximum and the critical voltage level. So let's start with the energy will intuition. Let's say we have X as a state. Take, for example, X as a vector. Let me write it down as a vector. Take, for example, let's think, for example, we have bus A, we have bus B, and here we are having what? Transmission line. We usually denote transmission line as an inductance, okay? Let's pretend that this transmission line, here we have VA phasor, here we have VB phasor. So what is VA phasor? Is magnitude times e to the power j, an angle, call it delta. And delta is in radians. So in your Python, you denote VA phasor as VA, a number, a real number. It could be 100 kilovolts. E to the power j of an angle. This angle in radian, it could be 0.1, it could be 0.2 radians, it could be pi over 2, it could be whatever. And VB is written as VB e to the power j. In this example, we're using 0 degrees. Sometimes bus A is 0, bus B is delta, it doesn't matter. So what are the states of the system? What are the states? What is a state? From control engineering, a state tells me the status of the system. In power system, we identify the states using currents. Yes or no? Is the current a state? No. Let's think about the pendulum example. Do you remember the pendulum? Is the speed of the pendulum a state or the position of the pendulum? Position of the pendulum. So why the position of the pendulum is the state? Because the higher the pendulum is, the more kinetic energy it is capable of delivering. If you leave the pendulum from an upper level, it will swing faster. If you leave it from a lower angle, lower position, it will swing slower. So in power system, what is the closest quantity that stores energy? It is voltage.
I was about to say it.
It is the voltage, that is correct. It is the voltage. So the voltage is where we store the information of the system. So having said that, this little v, this delta, this VB, this zero, store the information. So I can develop a matrix X or a vector that has the rotor angle delta, that has the bus voltage V. Sometimes we throw in a frequency, but I'm not going to do it. That's another way. But why frequency? Because each of these voltages come from generators at the beginning that has a certain frequency. If that generator was spinning 61 hertz, then what will happen is this will impact VA phasor, VB phasor. If that generator is spinning at 0 hertz, it becomes DC. Then this voltage will be DC, this voltage will be DC. Something like that. Think about it this way. So we store the information as a state. Sometimes we rely on voltages and angles. Sometimes we have VA, VB, VC. But it's voltages. It can be 5 voltages. It can be 4 deltas. It can be multiple frequencies of every bus of the system. So a bus is similar to communication. A bus is a collection of transmission lines where they meet. Okay? So let's say that the potential energy, let's define a potential energy U as a function of X, could be as a function of delta, V, and frequency. We have one of the 3 cases. The first case, in stability, the reason I'm explaining the stability is because we have to know what we're doing. Let's say we plot in this plot. Let's say we have delta. Let's say we are at this location. So any movement here would drive us to the bottom of the curve. Let's say this is delta. This is delta plus some epsilon. This is delta minus some epsilon. I'm changing the delta a little bit. If I change delta here, the system can go back. However, if the system is upside down, any small change in delta, it will deviate away. So that's what we meant by energy wind. We have stable equilibrium, ball up at the bottom of the ball, small perturbation create distorting forces, the system returns. Possibly with whatever impact, we can return back. The second case is unstable equilibrium. The third case is talking about slow evolution. What is meant here is as loading, the more we add loads in the system, topology changes. The topology change. We connected more lines. Or reactive reserves. We have a capacitor banks connected. Or shunt reactors connected. We change the set point of the generator. Or we add inertia mix, change slowly by adding renewable energy. Where there are inertia-less PV panels, they are bad when it comes to stability. They somehow mess around with the frequency. This will reshape these stability curves. Okay? It will reshape. So power system mapping we need to map the power system. Why? To study the stability. So why we're doing 520? To develop enough skills to assess the stability of the system. This might be a question in the test. YouTube, okay? Why we are doing an admittance matrix? Why we're doing per unit? Why we're modeling? Why? When you run a power flow, why you're doing it? To assess the stability of the system. So based on that, you can restore forces, such as, for example, you change the torque. So if the electrical power changes, how much, if a generator power changes, how much of that impact would change the delta angle of this voltage? The other thing is the excitation control and damping. That's very important to study. Now, what moves energy surface between states? Sometimes we have generation, load balance, and tie-line transfer. What does that mean is, if I'm putting more mechanical, PM, more mechanical power, how would this change with electrical power? If I change that topology, if I have transformers outages, if I have transmission line contingency, if this line is out of service, how would this impact the stability of my line, of my system? Even if I change the ratio of a transformer from 1.09 to 1.05, what will happen? Moreover, if I add, for example, FACTS devices or shunt, FACTS devices are added, they are flexible AC transmission systems. Or what if I add an AVR, automatic voltage regulators? What will happen if I change my control engineering? What will happen? So the energy or the potential energy will change. So what is the difference between steady state and transient? Well, steady state or static stability is capability to remain in synchronism under small gradual changes. So slow load increase, removal of a line. So these analysis, what we're going to do in 520, we're going to have linearized models, eigenvalues, synchronizing power coefficient, etc. Transient stability in other courses. Is there a course called transient?
Dynamic. There's a course called dynamic.
Dynamic?
Yes.
Dynamic is similar like transient. What will happen in between? It's 522, huh?
Right.
So what will happen in 522 is capability to remain in synchronism after large events. A big faults in the system. For example, faults, three-phase faults. Loss of large generator. So, if you recall in power system, what is this delta? If I have a simple two-bus system, delta will appear as the angle between bus A and bus B. Why this delta is important? Because it tells me how much real power I can transfer here. Using this equation, are you familiar? Have you ever seen this equation? VA, VB over X sine delta. Have you ever seen it? In the undergrad level 3 course, the maximum power occurs when delta is 90 degrees, because sine 90 is 1. And it is VA, VB over X. What is X? It's the reactance of the transmission line. So the more reactance of this transmission line, which is similar to the impedance, the less power you can transfer. So at 90 degrees, that's the peak. We usually operate way below 90s. We usually operate in this region. Well, this is not stable. So do not operate an unstable power system. This is illegal. You have to be legal. Stable. So we usually operate way below 90 degrees to retain the margin. So in the two-bus system, again, this is a warm-up slide. What is the electric current, I? It turns out I is calculated using what? VA phasor minus VB phasor over JX. Voltage difference equal I times the impedance. Ohm's law. Are you familiar with Ohm's law? So I equal VA minus VB over JX. Okay? That's very important. So here, what is the complex power? The complex power is that goes to usually bus B. So this is the source, this is the load. It's calculated using the equation VB times I star. What is star?
Complex conjugate.
I star is conjugate. It means flip every j
With minus
to
one.
minus j. J is the square root of minus 1. We will solve example later about it. So if you have the real power as this equation and the imaginary power, the reactive power as VB over x, VA cosine delta minus VB, somehow I can do some mathematical trick and I can eliminate delta. Why I eliminate delta? Because sometimes I may not be able to measure it directly from the system. Remember, delta is the torque angle of the generator. To measure the torque angle of the generator, you really need to have some optical sensors to see the angle of the rotor. But sometimes this is not feasible. So let's eliminate delta, do some math. Math is hard. We get this equation. How they did it? They used this trigonometry, sine square plus cosine square equal to 1. And this is the sine, this is the cosine, equate them to 1. Then you should have this number. And y is VB squared. So once you do the equation, we can have this equation. VB equals, I can write it as a function of VA, magnitude, not phasor, Q, reactance, P, and VA. So I can, by knowing the power flow in the system, I can predict the voltage level here. Why I know the voltage level here? Because if I don't have a stable system, this would have a voltage collapse. If a voltage collapse at the load, then what will happen? Customers will not have enough voltage to maintain the loads. We're going to have system collapse, blackout. Are you familiar with these terms? System collapse? So we can estimate VB using this equation by knowing the real and reactive power flow. Now, if you take the plus sign, you will have VB plus, which we will call it the upper solution. If you take the lower, this is the unstable branch, the lower voltage. You always want to have the voltage as high as possible, close to 1 per unit. Or the nose point, which is just this number by having this term to be 0. So the maximum reactive power, or real power, should be in this equation. I'm not going to ask you to memorize the equation. You will have an opportunity to create your own formula sheets when we ask the exam. Okay? So when does this occur, like the maximum power transfer? It occurs if this is greater than 0 and the two real solutions, they are two real, now complex number, operate in the stable branch. And if this quality holds, the derivative will be 0, so VB is equal to V critical, P is P max. So the maximum power transfer occur at the critical voltage. So at critical voltage, we have the maximum power. Okay? And if it's less than 0, no real VB exists, steady state equilibrium is lost. So what is this? What are the remarks on steady state and transient? What do we understand from steady state and transient? PV curves, which we're going to have a lot, they describe the static feasibility under slowly varying stress. If you change the operation slowly, how those PV curve. Transient stability looks at the big events, a big fault in the system. This is 522. In this course, we're going to have this load disconnected, this line is disconnected, small events that are gradual. So the automatic voltage control is slowly moving. Okay? So here, for example, there is some exercise I want you to practice and try to understand these codes. So here, for example, try to do it. Anybody knows how to plot Python code? What's the best tool? Colab? Colab should be, Google Colab, you can have Python and you can run it. Or you can use Spider if you have your own machine. So try to have these plots and see how they look like, and try to understand these libraries, okay? So in this course, our goal is to, instead of having calculators, let's use the Python to do all the calculations, okay? I still haven't thought about the exam. Maybe I will allow you to do coding in the exam. Let's go. Let's see how it goes, okay? But try to do these at home. It's very important. We have two curves. One is VB versus P for lagging unity, lagging and unity and leading Q. What is the Q? Yeah, we have Q is one is 0.2, one is 0, one is minus 0.2, and we have VA as 1, Vx to be 0.3. So we have 3 curves in this exercise. We expect to have 3 curves. The other exercise, I think it's the same, but here we are sweeping VB from 1 all the way to 0. Anybody sees where we do the sweep? Here. From 1 to 0, 500 steps. That's how to read these curves. So try to plot these curves and see how general PV curves look like. So what's the purpose of today's lecture? The purpose of today's lecture is 1, to get familiar with the course. 2, is somehow to introduce the power system stability. We really need to improve our skills in order for us to assess the stability of the system. I want you to think throughout the semester that I'm having 2-bus system. When I run the power flow, I want my system to be stable. Here I'm using these equations developed. So try to study these. If you have any questions, please let me know. And that is lecture number 1. We will go to the basic concept next week. This is a motivational lecture. This is not, of course we will have it in the exam, but it's a motivation. Why we're doing it. Remember, the why is the most important piece of a PhD. We are here to think. We are here to think. We are not here to memorize, for example, oh, this you have to put square root of VA power 4. We are here to think. How did they, I'm not the one who developed these slides, credit to Dr. Fahd Ismail. How did they think about using this basic trigonometry to reach up to this equation, escaping delta? Why we escape delta? Because you can't measure it. You can measure it with lasers, but it's something that is, if you are measuring the power in the system, the power flow, it can tell you the story without dealing with the delta. And in state estimation, dealing with angles is way much more difficult than dealing with the real power. Remember, when real power moves from A to B, there is money involved. If there is money involved between utilities, then there is no way the two of them make the same mistake. So that's why in power system, the power flow from A to B is usually quantified, and the utilities, they know how much power is moving from A to B. Okay? So do you have any questions about today's lecture or the course in general? So I will not use the blackboard. I will use OneDrive. Yes, you have a question?
I want you to clarify according to the stability of this curve. Why above TCE degree is unstable? Because sine 30 equal cosine.
Well, if you operate above 90 degrees in this region, you still can go back to stability. But how can I answer this question? What is sine of 100? Start having negative signs. Negative. So don't exceed 90. In power system, there is no delta larger. If you're 90, you're unstable. So most of the generators, they operate at a very small torque angle, 10, 5, 6 degrees. So if you have above 90, you will end up with negative numbers. It's gonna reverse the power flow. So don't do. That's one of the reasons. But I want you to know that if you have a curve like that, then this is not stable. So you have to make sure that you maintain this curve. Okay? Now, in this course, or where is the syllabus? In this course, we will start from next week about basic concepts. So what do I want you to do? Take the textbook and look at the titles. Take the textbook and open the titles of these chapters, 2, 3.2, 3.6, 5.2, 5.3, and try to familiarize yourself. If you are not familiar with any concept, try to have a very short introduction. We're not going deep now, okay? But try to have the textbook with you, and inshallah, during the semester, we will walk over enough examples, enough slides, enough material. So today's lecture is a little bit of shock that you have to do the work. So please, go ahead, do chapter 2, try to familiarize yourself with chapter 2, try to read all of these. You are grad students, you should read. Now, part-timers. If you are a part-timer, then I advise you to focus on the important things first. You may not have enough time, but try to watch the YouTube videos in your free time, okay? That's very important. So I'll try to upload the YouTube videos. Now, I really don't know if we exceed 1 hour, the camera usually turns off, so I have to think about an alternative setup. So, cameraman Mr. Muhammad Hussein?
Hassan al-Qurani.
Mr. Muhammad Hassan, always please monitor this. If it turns off, let me know, okay? We're gonna lose information. So, do you have any question about the course itself? Who's dropping? You drop. At least say goodbye, okay? Well, those who have core, there is no way to escape.
We are here to learn.
That's the thing. You know what's the best course I've ever taken? Optimal control. I took a B. Proud. Be proud. Proud. Be proud. That's what I call it. Get a B. I don't want you to get an A. I don't care. Get a B. B is the best grade because you will learn. A plus. It's good. Get it. But this is the best course I've ever taken in grad school. Optimal control. Okay? That's very important. You have to take it. So Hassan Mubarak is teaching it?
No, I think Dr. Ibrahim Brown.
Dr. Ibrahim. Okay. Okay, I'm going to check on your performance. Do you have any questions? Okay, let me turn off the camera.